You're watching NASA Television.
Manned spaceflight, a national heritage of exploration, made possible today by the Space Shuttle. The Space Shuttle is comprised of a delta-winged spaceplane called the Orbiter, an external tank which contains liquid fuel for the orbiter during ascent, and 2 solid rocket boosters. The shuttle is a true aerospace vehicle. It takes off like a rocket, maneuvers in Earth orbit like a spacecraft, and lands like an airplane. Unlike earlier space vehicles, the majority of shuttle components are refurbished and reused. Design and production of all booster components is managed by the Marshall Space Flight Center's Space Shuttle Projects Office in Huntsville, Alabama. Thiokol Corporation Space Operations and the USBI Company, a subsidiary of United Technologies Corporation, are contracted by NASA to build and refurbish the Space Shuttle solid rocket boosters. The boosters are assembled by Thiokol Corporation Space Services at Kennedy Space Center. The 2 boosters serve as the shuttle's structural support for stacking, rollout, and launch. The solid rocket boosters are the largest ever flown and are the first designed for recovery and reuse. The twin boosters are the workhorse for liftoff. They provide the equivalent of a 40 million horsepower motor and burn an average 9 tons of solid propellant per second. They provide 80% of the thrust needed to lift and accelerate the shuttle to approximately 3,000 miles per hour. Space Shuttle solid rocket boosters are comprised of 3 major components: a forward assembly, a solid rocket motor, and an aft skirt. The solid rocket motor consists of an aft segment which contains a flexible nozzle, 2 center segments, and a forward segment which contains the igniter. The aft skirt contains the thrust vector control system which steers the booster nozzle and the aft separation motors. The forward assembly contains a nose cap which houses the pilot and drogue parachutes, a frustum, which contains the 3 main parachutes and the forward separation motors, and a forward skirt, which contains booster power and electronic controls. Solid rocket motor manufacturing begins as high-strength steel cylinders are received for processing. 2 cylinders each are joined to form the forward and 2 center segments, while 3 shorter segments are joined to form the aft segment. Each segment is electronically scanned for cleanliness. Next, rubber insulation is applied in layers to the segment interior. The insulated segment is then vacuum bagged and placed in an autoclave. This serves to cure and bond the insulation to the metal case wall. Next, a lining material is applied to the insulation. This will later form a chemical bond with a solid rocket motor fuel or propellant. The propellant consists of a fuel of aluminum powder, an oxidizer of ammonium perchlorate, a burn rate catalyst of iron oxide, which gives the propellant its red hue, and a binding material. Once mixing is complete, the propellant is loaded into the motor segments through a process known as casting. For this operation, the casting segments are lowered into one of 8 casting pits. Casting takes place as the propellant mix bowl is placed over the segment and a vacuum is drawn. This forces the propellant into the segment interior and around the casting core. Once cast, the propellant is allowed to cure and harden. Cured propellant is similar in texture to the eraser head of a pencil. The core is then removed, leaving a bore through the center of the solid propellant. When ignited, the propellant burns uniformly from the center to the case wall. The metal case is protected by the propellant's own insulating properties. The forward segment contains an 11-point star-shaped propellant configuration, which provides high thrust for liftoff, then reduces thrust by 25% to minimize stress to the crew and vehicle. Once casting is complete, a nozzle is installed into the aft motor segment. The nozzle and aft exit cone control the 5,000-degree motor exhaust and are used to steer the vehicle during its first 2 minutes of flight. Many nozzle components are formed by wrapping carbon and glass phenolic cloth around a mandrel or steel housing. The components are vacuum bagged, cured, and machined to design specifications. At the center of the nozzle is a flexible bearing. This component includes layers of rubber bonded between metal shims. The flexible bearing is the vital component which allows the nozzle aft exit cone to pivot. Nozzle components are assembled in an environmentally controlled, clean facility. This stringent environment prevents even the most minute contamination from coming in contact with the nozzle assembly. Once cast and cured, the motor segments are moved to the final assembly work center and prepared for shipment to Kennedy Space Center. Preparations include X-ray inspection, segment weighing, and igniter installation. The igniter is a small rocket motor, which is used to start the burn for the solid rocket booster. At ignition, it sprays a burst of hot gas down the length of the motor, instantly igniting the exposed propellant surface. In order to verify motor performance, selected segments are assembled and tested. Flight segments are shipped to Kennedy Space Center on specially designed rail cars. The forward assembly and the aft skirt are assembled, tested, and refurbished at the Marshall Space Flight Center Assembly and Refurbishment Facility located at Kennedy Space Center, and at the Booster Disassembly Facility located at Cape Canaveral Air Force Station. The aerodynamically shaped forward assembly contains the electrical and instrumentation systems critical to booster ignition, separation, re-entry event sequencing, and recovery. Major forward assembly components include the nose cap, the frustum, and the forward skirt. The nose cap contains the pilot and drogue parachutes which orient and stabilize the booster for controlled descent. The nose cap is the only major booster component not recovered and reused. Work begins on the frustum and forward skirt as insulation is applied to all external surfaces. The insulation protects both structures from aerodynamic heating during flight. The frustum contains the forward separation motors, the altitude sensor assembly which initiates both drogue and main parachute deployment, thrusters used to separate the nose cap from the booster, the frustum ring detonator used to separate the frustum from the forward skirt, and the three main recovery parachutes which slow and control booster descent for soft water impact. The forward skirt provides an attach point for the parachute floats and the main recovery parachutes. It contains the integrated electronics assembly, which controls all booster electrical systems and distributes orbiter commands for booster ignition and separation. The forward skirt also contains the rate gyro assemblies which provide guidance data to the orbiter during ascent, sensor timing units designed to initiate nozzle separation and main chute disconnect, and a flight camera to provide a photographic record of main parachute deployment for post-flight analysis. Once processing is complete, the three major components are connected to form the forward assembly. Finally, an automated booster assembly checkout system provides diagnostic testing and pre-flight verification of all forward assembly electrical and instrumentation systems. The exterior surfaces of the aft skirt are insulated to protect metal components from the 5,000-degree motor exhaust. Technicians then assemble and install the thrust vector control system. The thrust vector control system consists of two hydraulic power units, each of which includes a fuel supply module, an auxiliary power unit, a hydraulic pump, and a servo actuator. During operation, pressurized hot gas is formed when hydrazine flows from the fuel supply module to the auxiliary power unit and across a preheated gas generator catalyst bed. Within 4 seconds, the pressurized gas spins up the auxiliary power unit gas turbine to 72,000 RPM. The turbine drives a gearbox, which in turn powers a hydraulic pump. The pump delivers hydraulic fluid to the servo actuator pistons at a pressure of 3,050 pounds per square inch. The servo actuators, connected between the aft skirt and nozzle aft exit cone, then pivot the nozzle and steer the vehicle in response to orbiter command. Insulation foam is used to protect the thrust vector control system and aft skirt interior from the radiant heat generated by motor operation and from the loads incurred at booster splashdown. The aft skirt also includes the aft separation motors. Once aft skirt assembly is complete, the automated booster checkout system is used to assure proper actuator response under flight conditions, commonly referred to as a hot fire test. Solid rocket motor segments and aft skirts are first received at the rotation process and surge facility. Here, the aft segment is rotated to the vertical and attached to the aft skirt. The exit cone is then attached to the aft segment. An external tank attach ring is then positioned around the aft segment and fitted with 3 struts which connect the external fuel tank to the solid rocket boosters. The aft integrated electronics assembly is then installed to the attach ring. This device distributes orbiter commands to the thrust vector control system. Once processing is complete, the aft booster is taken to the vehicle assembly building and positioned on the mobile launch platform. The 2 aft skirts will bear the total weight of the shuttle system, about 4.5 million pounds. 4 hold-down posts are installed through the aft skirt to the mobile launch platform, secured with frangible nuts and tightened. The hold-down posts lock down the booster stack to the mobile launch platform. At the instant of liftoff, an ordnance charge in each of the frangible nuts explodes, releasing the aft skirt from the mobile launch platform. The remaining motor segments are then individually stacked. Finally, the aerodynamically shaped forward assembly is joined to the forward segment, completing the booster. The external tank is attached to the solid rocket boosters with rings and struts, which release upon booster separation command. Once the orbiter is attached to the external tank, the shuttle is rolled out to the launch pad and prepared for launch.
10. We have a go for main engine start. 6, 5. We have main engine start. 3, 2, 1. SRB ignition and liftoff. Liftoff of SDS-29 as Discovery clears the tower.
About 2 minutes into flight, a pyrotechnic charge is detonated at the forward attach point and aft struts, and the forward and aft booster separation motors are ignited. Once released, the boosters coast upward for an additional 70 seconds before falling toward the ocean. At 16,000 feet, the altitude sensors initiate nose cap release. The pilot parachute is deployed, pulling out the drogue chute. The drogue chute decelerates and orients the booster. At approximately 6,000 feet, the frustum is released, deploying the main parachutes. This slows the boosters for safe water impact. Just prior to splashdown, a portion of the aft exit cone is severed. This reduces impact loads to the solid rocket booster nozzle. At impact, the parachutes and floats are released. Meanwhile, the retrieval ships are positioned to recover the boosters. First, the main parachutes are reeled on board. Next, the frustum and drogue chutes are retrieved. Divers then plug the nozzle of each booster. As air is pumped into the motor interior, the boosters rise and tumble to the horizontal. The boosters are towed back to the disassembly facility at Cape Canaveral Air Force Station. All recovery and refurbishment activities here are managed by the Marshall Space Flight Center's Space Shuttle Projects Office. Once the boosters have been positioned in the recovery slip, they are lifted from the water and rinsed to remove saltwater contamination. A robotic hydrolaser is used to remove insulation from the booster joints, aft skirt interior, and forward assembly. Major components are then disassembled. Here, NASA, USBI, and Thiokol engineers thoroughly assess the booster components for damage. The parachutes are returned to the parachute refurbishment facility, where they are processed, refurbished, and repacked. Smaller booster components are processed on site at the disassembly facility or at various vendor facilities. Unique robotic systems are utilized to remove and reapply the multi-layered thermal protection coating from the forward assembly and aft skirt. These robotic systems were developed specifically for SRB component refurbishment. They provide increased safety, greater precision, and a 90% savings in the time required by manual operations. Motor segments are returned to Utah, where they are further disassembled, cleaned, tested, and returned to the manufacturing area for recycling. Post-flight data evaluation is performed at the Marshall Space Flight Center and USBI facilities in Huntsville, Alabama, and at Thiokol Space Operations in Utah. NASA Space Shuttle team members are dedicated to the safe, reliable, and cost-effective production and assembly of solid rocket booster components. This combined effort reflects NASA's commitment to quality at all levels of production. As we look into the 21st century and beyond, it is clear that the Space Shuttle will remain as a workhorse for building and expanding the frontiers of technology.